Have you ever wondered what makes the physical world hold together so perfectly? We usually just think about the shape of things we can actually see, right? But down at the microscopic level, there are these hidden invisible rules governing exactly how molecules behave, interact, and ultimately survive. Welcome to This Explainer. Today, we're unlocking one of the absolute coolest secrets in all of chemistry. It's this concept called aromaticity. Now hold on, if you're thinking this is going to be a lesson about how your favorite perfume or your morning coffee smells, prepare to have your mind blown. We are going to look at how a term that literally started with our noses evolved into a rigid, mathematical law that dictates the stability of the universe's most important building blocks.
So here's our roadmap for today. First, the meaning of aromaticity. Second, cracking Huckel's famous rule. Third, the unstable anti-aromatics. Fourth, expanding the aromatic family. And finally, number 5, why aromatic molecules matter.
All right, Section 1, the meaning of aromaticity, from smell to science.
Let's dive right in by looking at where this whole concept actually began, because it's honestly a classic case of scientific misunderstanding turning into something completely incredible. So back in 1855, a chemist named August Wilhelm Hofmann started informally using the term aromatic to describe a very specific class of benzene compounds. And why did he do that? Well, simply because they had really strong distinctive odors compared to other pure saturated hydrocarbons. At that point in time, amazingly, we were basically classifying the microscopic world using our noses. Crazy, right? But you know, science evolves. By 1931, the German chemist and physicist Sir Erich Heckel completely flipped the script. He moved us away from human senses and straight into hard physics, proposing a strict mathematical theory to figure out if a molecule actually possessed these special properties.
So what does aromaticity actually mean today? Well, in modern organic chemistry, it has absolutely nothing to do with scent. Zero. Aromaticity is actually a chemical property of a cyclic, which just means ring-shaped, and planar, or a completely flat molecule. These specific structures have a continuous ring of resonance bonds. Basically, electrons are just freely sharing space, zooming around the entire ring. And here's the absolute key takeaway. This specific arrangement gives the molecule incredible armor. Seriously, these molecules are incredibly tough. They do not break apart easily at all. In fact, they much prefer what we call substitution, basically swapping out one little part rather than adding new things in, because that precious, highly stable ring just wants to stay totally intact.
Now, obviously, things like wintergreen oil, cinnamon, and vanilla are classic aromatic compounds, and yeah, they happen to smell absolutely fantastic, but honestly, that's purely a coincidence of how they interact with human olfactory receptors. As a general chemical property, aromaticity bears absolutely no relationship to how a compound smells. It is all about that underlying structural armor we just talked about.
Okay, Section 2, cracking Huckel's famous rule, the VIP Club.
So how exactly does a molecule get this structural armor? How does it actually gain entry into what is essentially the ultimate VIP club of molecular stability? Well, it has to pass a really strict test. To be considered aromatic, a molecule must meet 4 non-negotiable criteria. First up, it must be cyclic. You absolutely need a closed ring of atoms. Second, it has to be completely planar, meaning all the contributing atoms are lying perfectly flat in the exact same plane. Third, it must be fully conjugated. That means there has to be a p orbital at every single atom in the ring to allow those electrons to fully flow all the way around. And fourth, and this is the real magic password here, it must have exactly 4 n plus 2 pi electrons.
This magic password is what we call Huckel's rule. It's a simple formula, 4n plus 2. In this equation, n is just a simple integer. It can be 0, 1, 2, 3, and so on. So, if we just do the basic math, a molecule needs 2, 6, 10, or 14 pi electrons delocalized around its ring to achieve ultimate stability. It's this beautifully simple mathematical code literally dictating the architecture of the microscopic world.
Moving on to Section 3, the unstable anti-aromatics, the chaotic twin.
But wait, what happens if a molecule looks like it belongs in that VIP club, but it shows up with the wrong password? Well, this brings us to the chaotic, highly unstable counterpart of our story. The really crucial point here is the sheer difference just a couple of electrons can make. If a molecule is cyclic, flat, and fully conjugated, but it happens to have 4n pi electrons, meaning 4, 8, or 12 electrons, instead of 4n plus 2, it's classified as anti-aromatic. Instead of being perfectly stable, this molecule is highly unstable and incredibly reactive. It has a significantly higher energy state. It's almost like the molecule is just trapped in a state of extreme tension.
And this brilliantly illustrates just how much nature hates instability. This anti-aromatic state is so energetically punishing that molecules will literally bend and contort themselves completely out of shape just to escape it. It's basically molecular yoga. By twisting and becoming non-planar, they intentionally break that flat ring of p orbitals, literally destroying their own conjugation just to avoid the dreaded 4n rule. It's molecular self-preservation in action, and it's wild to think about.
All right, Section 4, expanding the aromatic family, beyond benzene.
Now that we totally understand the rules of the club, let's take a look at the guest list, because it is way more diverse than just simple rings of carbon. While benzene is definitely the classic example, aromaticity extends so much further. Think about heterocyclics like furan. In that case, an oxygen atom steps in to take the place of a carbon in the ring, cleverly using its own lone pair of electrons to complete that strict 6pi electron requirement. It's like a really clever loophole to get into the club. Then you have substituted aromatics. This is where we take that super stable benzene ring and attach other functional groups to it. This creates some incredibly important real-world compounds, everything from the pain-relieving magic of aspirin all the way to the explosive power of TNT.
And it gets even cooler when we start actually combining these rings. We call these polycyclic aromatic hydrocarbons. Think of them almost like molecular honeycombs. Molecules like naphthalene, which you might actually know from the smell of mothballs, or anthracene, are created when two or more of these aromatic rings literally fuse together, sharing neighboring carbon atoms. And the amazing part? They still maintain that cyclic, conjugated pi system that keeps them incredibly stable across the entire expanded structure.
Also, the club isn't just for neutral molecules either. Even charged particles, or ions, can achieve aromatic stability. Take the cyclopentadienyl anion, which carries a negative charge, or the cycloheptatrienium cation with its positive charge. As long as they are planar, cyclic, conjugated, and perfectly hit that 4n+2 electron count, they are welcomed right into the fold with all the amazing stabilizing benefits of aromaticity.
Finally, Section 5. Why aromatic molecules matter, scale, and impact.
Okay, all of these rules and structures are scientifically fascinating for sure, but why does this actually matter to you and me in our daily lives? Well, let's zoom out and just look at the sheer scale of aromaticity in our world, 35 million tons. That is the staggering amount of key aromatic hydrocarbons, things like benzene, toluene, and xylene, that are produced worldwide every single year. Extracted from complex mixtures of oil and coal tar, these highly stable molecules are literally the indispensable backbone of modern industry. They're the starting materials for the plastics you use every day, the nylon in your clothes, essential chemicals, vital polymers, the whole shebang. Without the stability of that simple chemical ring, modern manufacturing would just grind to a complete halt.
But you know what? It gets even more personal than that. Aromaticity is quite literally the foundation of life itself. 4 of the basic amino acids that build the proteins inside your body right now rely on aromatic rings. All 5 of the nucleotides, adenine, thymine, cytosine, guanine, and uracil, that make up the genetic code in your DNA and RNA are aromatic purines or pyrimidines. Their aromatic stability is exactly what keeps your genetic code from just falling apart. And look at heme, the molecule in your blood that carries oxygen. It relies on a massive aromatic system of 22 pi electrons. Even chlorophyll, the stuff that allows plants to harness energy from the sun, utilizes a very similar aromatic system.
So armed with all this, you can now start to really see the hidden matrix of the molecular world. You know that to spot the incredibly stable aromatic molecules, you aren't trying to sniff out a smell. Instead, you're looking for flat, unbroken rings containing 2, 6, 10, or 14 freely moving electrons. And of course, you know to watch out for those dangerous, super unstable anti-aromatic compounds cursed with 4 or 8 electrons. You are literally seeing the secret structural codes of chemistry.
It's truly amazing to think about, right? A simple, totally elegant mathematical rule, 4n+2, dictates whether a molecule will violently react or remain stable enough to carry the very blueprint of human life. It really makes you wonder, if the stability of our DNA, the effectiveness of our medicines, and the literal materials of our modern world all rely on this one invisible law of physics, what other mathematical codes are secretly running the universe just waiting to be discovered? Thanks so much for joining me on this explainer, and keep questioning the hidden rules around you.